Well, it's a pleasure to be here. This is going to be a low-tech talk. And in terms of LTER, I was actually on the LTER executive committee when that was first proposed. And ARS and LTER are culturally very different. And it's really been an interesting fit trying to bring these two together. And so I got asked to just talk about my research experiences and insights from being involved with a lot of these long-term in-situ network programs. And the start really was in the early 80s, mid-80s, with the Emerald Lake project in Sequoia National Forest. That was the first project that was large, interdisciplinary, in high mountain environments. And I just want to give a shout out to Kathy Tonneson, who was the administrator that really made that happen. And two things that came out of it that were interesting is Kelly LTER developed protocols for snow hydrology measurements that we still use today. I developed protocols for snow chemistry measurements that we still do today. And that's one of the advantages of sort of big science. All right, and then that involved into NASA EOS, which Jeff is here. He was the PI on it. It was $7 million in 1991, the largest environmental science grant at that time. And again, it was to study the hydrology and hydrochemistry of high elevation, seasonally snow-covered basins. One of the takeaways from that was data management was a huge challenge. The tools weren't very good back in those days, but it's still a problem today, as people have talked about. But here's the biggest insight I got from that program. So we had a site review from NASA. The grad students, I was a grad student, put most of the material together. We presented our material. We're really nervous about the feedback from NASA. What did they ask? How can you help us sell EOS to Congress? And I realized that's how you do big science. You have to convince people. So the takeaway message for me is that you have to work with your science community and your funding agents to get sort of big science, in situ long-term networks to happen. You got to have a vision. You got to be persistent. And I'm going to give some examples of that. All right, I'm the PI on the Niwot Ridge LTER project. There are 25 LTER sites, soon to be 24. So we've lost 2 sites over the last 4 years. One of the outstanding questions is how do you actually maintain and manage long-term research? And right now the LTER program is essentially negotiating with NSF because we have different divisions. Keeping these long-term networks going is really difficult. All right, why LTER? This started in 1980, Niwot Ridge. It was actually one of the first sites funded. And it's because science doesn't happen in nice 2 or 3 year increments, which is the funding cycle for a master's student, right? Doesn't happen always in 2 or 3 years. And so you need long-term data, which is what Tillman illustrated with this graph here. All right, so LTER started in 1980. It's been really successful. We're up to 26 sites. We're now segueing down to 24. We still have to figure out the administrative structure. It's difficult. But in terms of the pros, great science. Long-term data really matters. You can ask more sophisticated questions with long-term data. It leads to interdisciplinary research. You get your scientists out of their disciplinary silos, which I think is an incredibly important component and result from LTER. And we do a pretty good job of making that data available to the public. And in fact, the case has been made, I've made this, other people have made it, that the gold standard for environmental data and making that environmental data is the LTER program. Hey, that's nice, that's good. The bad is we don't have a good data set or a good data management system. All right, so the cons of LTER, because it's a bottom-up, as people have been talking about, no consistent methodology. Deb mentioned NPP. Different sites collect NPP differently, so you just can't mash them together. There's no consistent instrumentation. Each site has its own data presentation, though we are trying to move towards an integrated data management system. It's not here yet. And all that makes cross-science synthesis and interpretation, scaling to regional and national scales, very, very difficult. All right, so GEO in 2007 started its sort of analog to LTR, which was CZOs. We've heard a little bit about them. And the idea with CZOs is to provide the basis for advances in multiple Earth sciences. CZOs are data-rich places to develop and test Earth models. And so here's the difference between LTER, which is in bio, CZO, which is in geo. They're both in NSF. NSF Bio has told us LTRs are not research platforms. So there's some interesting problems with running these long-term networks. So what the hell is a CZO? We always get that question. The critical zone is where water, atmosphere, ecosystems, and soils interact on a geomorphic and geologic template. All right. When CZOs got started, the PIs got together, and one of the things that they've really tried to do working with NSF is respond to some of the deficiencies of LTER. They're trying to come up with consistent instrumentation at each site, consistent methodologies and protocols. When CZO got funded, in the funding letter, NSF said you had to have a centralized data management system. That was not in the call. There was no money for it. Boulder Creek, which includes 9-watt LTR, was one of the first 3 sites. And I was at the initial meeting. I put my hand up and I went, "You can't do that." And they went, "Who are you?" So my name's Mark Williams. And they go, "Why can't we do this?" Because it's an unfunded mandate and it's expensive. So I worked with NSF then to come up with funding and come up with a centralized data management system, an integrated data management system. So here's our schematic. Got funded 2 years ago. I was a PI. And the biggest problem is at the bottom. How do you get data from the scientists to the site data manager and from the site to a centralized network? There are tons of smart people that can write code and do good things with data, but you got to give it to these people in the right form with the right format. And so what the PIs did, to their credit, because this was not in the initial response, was agree to develop protocols for presenting that data at each of the sites that were similar, so it's easy to harvest them. And I won't walk you through this. I actually had to step down as PI because I hate to say this. I hope there's no NSF people in the audience, but I got overfunded. And I'll end with that. And part of that was actually developing the integrated data management system. That's like a lot of work. So I walked away from it, gave it to somebody else. All right, so that brings us to NEON. LTR is 9-watt LTR is a NEON core site. And NEON was actually developed by LTR scientists who were on rotation at NSF to answer questions at the regional and national scale, realizing that we can't do it with the bottoms-up LTER structure. And here's a history lesson. I don't know if Brian's seen or other people. Oh yeah, just one thing. So here's NEON domains. They have their own acronyms and vocabulary and all that. Our site is the only high elevation site, 11,400 feet. David just talked about good personnel, good planning. NEON started construction this summer. Right now the site's under a couple of feet of snow. Can't get to it. And they've abandoned equipment up there because it actually snowed and they weren't ready for it. But you get it, you do it for a couple of years. There's a learning curve. All right, NEON. 2002, $55 million in the president's budget for NEON. And that was for the first 2 sites. Hosted a workshop in Boulder. And after that, we wrote an FP in my office because it was right next to where the workshop was with Schimmel, Russ Monson, Scott Collins. I mean, we were totally fired up, excited, wrote the RFP in like a day and a half. And then no money was taken from NSF, but $55 million was taken from bio and put into physics. The physicists know what they're doing. They're very good at lobbying. So you got to play at that scale when you do this. 2005, 2006, $2 million pre-proposal to plan a real NEON, and they flunked the review in 2006. I was one of the reviewers. And I had drunk the neon Kool-Aid, pure and simple. And what they had put together just did not fly. And to NSF's credit, they just restructured, and a year later, it was essentially up and running. And that restructuring, is, to me, is, I still don't quite understand it. I was somewhat involved. They did an amazing job. So this is a timeline from 2007, and NEON is only 4 years behind for the start of construction. But that's the reality of doing big science and starting networks. A lot of that problem came from NSF because they didn't know how to do this. And all of a sudden, they got scared and started bringing in all kinds of new restrictions and regulations and all that kind of stuff. Brian definitely knows about that. All right. I think I titled this, which you guys skipped the first slide, What a Long, Strange Trip It's Been. And this is a NEON official slide, and I think you have to listen to the Grateful Dead to be a NEON employee. And of course, Hank Loescher is was the second employee hired. I'll just leave it at that. But we want to move towards sustainability, and that's really the goal of NEON. And by having good information, that's information that can help inform decision making. NSF is trying to go towards sustainability, so they have a new program called Sustainable Research Networks. I'm a co-I or co-lead on one of the two that got funded, $12 million, which is why I had to get out of CZO. And the goal here on our project is routes to sustainability for natural gas development and air and water resources in the Rocky Mountain region. One of the things that we're working on is air quality. We partnered in a recent Front Range experiment. This is totally cool. Front Range air pollution and photochemistry experiment. What's over the E in an experiment? An accent mark. It's an acronym with an accent mark. That's cool. All right, so what we've done is what we do as scientists, we've been everything. So we got a water quality team, we got a water quantity team, we got oil and gas infrastructure, air quality, human health effects. But the key here is we want to move this project towards sustainability. So we want to evaluate the economic and environmental trade-offs from fracking to give that information to decision makers in a way that informs decision making. And so we have a team here that is what unites everything. Social ecological systems analysis. Nobody knows how to do that. Our team has imploded. I'm now taken over as the lead, and I'm trying to rescue it. I mean, it's just a really difficult thing to do. That's where we need to go, but people don't really know how to do it yet. All right, so I'm going to end with two slides I stole from Jeff Dozier, but not really because he's right here. But really what we want to do is go from data to information to insight, which is increasing value. So this graph was done for hydrologists for the, water, and I'm a hydrologist who also does biogeochemistry. Lots and lots of people have contributed to making this slide. The bottom line is monitoring, collation, quality assurance, sometimes done well by many groups, but can be vastly improved. Aggregation of that data, distribution, as we've seen today, it's really not done well at this point, but at least we're moving in that direction. And what we really want to do is, with that data, is integration, analysis, reporting, and forecasting, all of which is not done well today. And this is my last slide, and this is Jeff's stuff, which I quite like. You know, we want to protect ecosystems and better manage and predict water availability and quality, looking from a water theme. And what drives the data collection and the data synthesis and interpretation is big science questions. So we need to have that, but really where we want to go from a sustainability area is the box on the right. How will human behavior, policy design, and institutional decisions affect and be affected by changes in water, in oil and gas development, or whatever? We don't know how to do that yet, but that's where we want to go with these long-term in situ networks. Thank you.